So as we're all probably relatively aware of, we can certainly have stochastic systems where we get this bimodal behavior, this multi-state behavior. The most obvious example is if we have a disease and we have a relatively low initial transmission rate and potentially a low number of people initially having the disease, well, there are usually two options. One is that the disease can take off and we start to get epidemics and maybe later on endemic behavior, or those infected people will just recover without infecting anybody else and the disease just dies out. And those two are very, very different circumstances, but can happen for, if we take one parameter set and we run it 100 times, maybe 40 times the disease will take off, maybe 60 times it'll die out. And any of the approaches we've described so far aren't necessarily going to be able to deal with that very well, because all that would necessarily happen is that we would be trying to treat all 100 repetitions of the model as being of the same class and trying to do something sensible with them, which seems odd. So we can actually show that with the model we've been playing with. All we really have to do, this model has been kind of chosen, particularly the choice of the transmission parameters, those 3 transmission parameters we set up, they've been chosen to try and enforce this sort of bimodal behavior. So all we have to do is run the time a bit further. So whereas before we were doing times 25, 40, 100, 200, we're going to add a few more times in there just to demonstrate this. And you're welcome to run this code. It runs a little bit longer for obvious reasons, so I wouldn't lose your mind trying to run it as we're speaking, and I'm not going to leave a sort of 5-minute gap for you to run it because it'd be unrealistic to do so. But we can kind of run this forward a bit longer. We can again plot the results, so we could plot the infecteds and the recovereds, and we get this sort of behavior. Now, the first half of this is fairly familiar. This is the kind of behavior that we got with the stochastic side, the variance emulation side. We have a spread of runs. This is for one parameter set. The stochasticity is quite clear. Now, when we get to time 270-ish, basically when this beta 3 parameter kicks in, whether the disease takes off again all depends on how many people we've still got infected in the system. So some of these are going to take off again once the transmission rate increases. We're going to get another little wave, and then it's going to dip back down. Quite a large number of them, and it's hard to tell because they're all sitting on top of each other here, quite a large number of them just die out. There is no new infection. And this green line here at the very bottom corresponds to this big bulk of blue lines here. So a lot of these are dying out at this parameter set, and only a small number of them are taking off. But this plot kind of highlights what I'm trying to say here. Well, up to t equals 270, we can treat this much the same way as we have done. We accept that there is some stochasticity. We model the stochasticity using the variance emulators. That allows us to make informed statements for our mean emulators to do something clever. If we try to do the same here and we just treat this band of blue lines as the same as this band of blue lines, what's going to happen is, well, the stochasticity is going to be assumed to be massive because the range of values that we can get is quite large, and that's going to inflate the variance by quite a way. And also, if we try to train a mean emulator to this spread of runs, well, we're going to end up somewhere in the middle here. So what we get out is an emulator that's predicting values that actually we never obtain with such a large variance that it's fairly meaningless. So this is something that we kind of had to worry about. And obviously this is not the case for all disease models. It's not even the case for all initial conditions for a single disease model, right? But when it does happen, we need to be aware of it. And it felt like something that we needed to worry about. So how do we deal with this in HMER? Well, the good news is, it doesn't really change much from the point of view of using it. So we have the same sort of setup. We set up some design points. This is all very, very familiar to us having done the sections 3 and 4, etc. The only difference here is we set up a few more targets because we're going to be modeling at later time points. Our initial points correspondingly are going to have more outputs, and our output names are going to be there's going to be slightly more of them. This is all kind of standard sort of thing. This looks much like it would do if we were doing any other model with more outputs than what we've been considering so far. Big difference comes when we're training it. Well, again, we've just taken all the realizations, all the repetitions that we've got, and we've stuck some into training, some into validation. And when we want to train these bimodal emulators, what we're going to do is we're going to use emulate from data again. We're going to give it all the training points. We're going to give it our output names. We're going to give it our ranges. So far, so standard. And we're going to change the emulator type to be multi-state. So what this does behind the scene is, well, with the variance emulation, what we said was that internally it was doing all this partitioning off into different parameter sets in order to make estimates about variances, fourth order quantities, etc., etc. When we set emulator type to be multi-state, there is an additional step before that where it tries to split up these repetitions, tries to identify which outputs have any bimodality, and for those that do, which parameter sets display the bimodality in that output. So it tries to subdivide these parameters into things that are bimodal and how often they are bimodal and which mode they sit in. So from the point of view of sort of running this, it looks very much the same. It takes a tiny bit longer for one reason, which is that we are now emulating both of these modes separately. So when we look back at this plot, what we're effectively doing is we're taking this big band of runs as being one mode, we're taking this band as being another mode, and we are training variance and expectation emulators to each of these individually, which means that, for example, this one, the mean will sit somewhere in the middle with relatively small stochasticity, relatively small variance. This one probably has a little bit more variance, but the mean will track this actual mode much more accurately than if we were to ignore it. And particularly, this tends to become important because if we're modeling this, and this is, I don't know, kind of an anthropic principle to it, if we're actually modeling this disease, chances are we're modeling it because it took off. So even though these represent a smaller set of the repetitions, small set of our realizations for our model, these are actually the ones of interest. So the natural sort of, the halfway house will be just to emulate one of these modes, but that actually doesn't tell us everything that we want to know. And there's a particular part, which I'll mention in a second, which becomes, kind of crucial. So what emulator from data does when we give it this multi-state argument is it's going to produce 4 sets of emulators, technically 5, but I'll talk about the 5th in a second. So for each mode, so we have a mode 1 and a mode 2. For each mode, we're going to have an expectation list and a variance list. So it's almost like the deterministic one gives us a list of emulators. The variance emulation gives us a list of 2 lists of emulators, 1 expectation, 1 variance. The bimodal emulation gives us a set of 2 lists of emulators. So it's kind of this stacked hierarchy of emulation. There is one other emulator that we get, and it kind of ties into what I was just saying. Well, actually, we probably care about how often that particular parameter set results in the mode that we want. And there's an easy way to do that. Well, at each of the training points, we can work out what proportion of those realizations ended up in mode 1, which we'll say is die out, against mode 2, which we'll say is takeoff. We can do that for all our training points. This is just information. This is effectively just another output of the model, which means we can emulate it. So alongside creating the emulators for the mean and for the variance of this system, we can also create an emulator which encodes the proportion of realizations live in each of those modes across the space. Okay, so again, the function is very similar. We give it very similar stuff. The output looks different. It's got a different structure to it than perhaps we'd be used to with the variance emulation and the deterministic emulation, but fundamentally it's all the same sort of thing. And a lot of the functionality of the package has been built to deal with it as similarly as possible to variance emulation, deterministic emulation. So we can do all the same sort of plotting. And again, we're using emulator plot just to get a look at it. We pick a couple of parameters. We fix all of our values at our chosen parameters. We don't see a huge amount of fun information here based on where our training points are. We've not got many points close. So this has a vaguely linear form, right? We can see that this particular output is probably linear in alpha and mu, hence the pretty straight lines running across. But what's important is this is for our first mode. If we look at our second mode, well, we actually get vastly different behavior. And it doesn't necessarily look like it's vastly different initially. Again, we've not been hugely influenced by data because there's no training point close by. But actually, the fact that there is no change as we vary mu tells us that in this second mode, mu is not active. Mu is not actually doing anything. There is a qualitative difference between these two modes that if we hadn't treated them differently, we just simply wouldn't have noticed. So we can see even from a relatively simple circumstance where these are just linear models and they're not really being influenced by data in this particular slice, there is a large difference between these two modes, especially when we start to look at where the maxima of this lies. If we look for the lightest color, well, the values are broadly similar. I mean, that's about 10% higher than the other one. but there is a much larger band where we can get this maximal value in mode 2. We can also do emulator plots with the proportion emulator. Like I said, it's just an emulator, and this can tell us how frequently we live in mode 1 versus mode 2. So we can plot the proportion emulator just the same as we usually would do. We can get the emulator expectation out. We can look at what this is. This is now effectively a proportion, so we'd expect it to live somewhere between 0 and 1. It's not strictly bounded by 0 and 1, despite the fact that it's a proportion, because this is an emulator, so we have a statistical approximation, so it could go slightly negative, slightly above 1. Not really the end of the world. This is just giving us a feeling for where we are most likely to live in each particular mode. And this is telling us, well, all of these are greater than half. So the chance of being in mode 1, which was our die out mode, is always, at least over this slice, higher than being in the takeoff mode. But there are some regions where it's more likely to die out than others. So all of this can give us information, again, into the sort of how our disease behaves, how our model behaves at different parameter sets. There are a couple of bits that kind of almost matter a little bit, and this now feeds into where suggestions are helpful. The first one is implausibility. Well, we need to think carefully about how we define implausibility now, because up until this point, we've had a whole host of emulators. We've gone, okay, calculate the implausibility univariately across all of them. We'll take the maximum implausibility across them. That's the job done. Here, we have to start thinking, well, if we've got two modes, how do we decide whether a point is actually valid to our targets? And the natural first approach is to say, well, if a point is not ruled out as implausible by at least one of the modes, then we have to keep it. So we can't rule a point out if one of our modes would say, actually, this would potentially fit the data. So what emulator plot and anything plausible by extension does when it's passed by modal emulators, note that we've not had to do any splitting or any subsetting or anything like that. It does pairwise minimization of the implausibility across the modes, and then it does the usual first maximum, second maximum, whatever. But in any event, it's still, we can still sort of see the usual sort of structure. This is over the same slice, and we can see that, this region is probably the most likely. Again, these are similar targets to the ones we've had before. So this has a rough similarity to what we saw in the variance emulation case. Again, there are a couple of bits for you to play with. Feel free to play with them, I say at home, if you ever have any time or the inclination. Diagnostics work exactly the same way. We can just pass it the full set. There is one small caveat, which is always worth bearing in mind, which is that were we to actually try and count all of these, you will note that there are twice as many as we'd expect there to be. So we've got 50 points here. I'm going to say 50, it's probably 50. We've got 50 validation points, and there are going to be 100 of these error bars. The reason for that, of course, is that we are checking both of the modes. So for any of the validation points, we do this similar sort of splitting into mode 1 and mode 2, and we make the comparisons with respect to the relevant mode. Thank you. So we often get, it's not quite so clear in a lot of these cases, but there's often a split in these diagnostics where the left-hand side is going to be the mode 1 side and the right-hand side is going to be the mode 2 side, or vice versa, because we're making this comparison across both modes. We want both of these sets of emulators to be valid because they both feed into proposing points and checking plausibilities, etc. But otherwise, these plots are all the same. From the point of view of using them, you just put all of your emulators in and it will do the work for you. And finally, proposing points is exactly the sort of same. From the point of view of doing anything, it looks identical. We just give it the list of emulators, it spots as mode 1, mode 2, it spots within that, there's variance and expectation, and it deals with everything accordingly. So these lines of code, feel free to play around with them to check what happens. What you will find probably is that there's a reasonable amount of restriction in the space that we had the variance emulation, and it goes a bit wobblier at high time because the particular mode we want is actually the one that's high stochasticity.